All right, coming to you live here, hands and all. We're in section 2.2. We're going to be talking about tangent line equations some more today, and then basic derivative rules. So that'll be a new adventure. So I want to kind of let you know that in calculus, we're very much obsessed with point-slope form. Now, not every answer is going to come in this format. Sometimes we take it and turn it into y equals mx plus b. But ordinarily, it's very easy for us to figure out x1, y1, and then calculate the slope. So that is why we prefer this format. Okay, so down here, let's try a couple examples graphically with this second obsession, right? Writing equations of tangent lines, okay, in point slope form. So we've got an equation here, y equals negative x squared plus 2x minus 1. And then we've got this point right here, 2, negative 1, right? And we're going to find the slope of the tangent line there. So like we did the other day, we're going to kind of count out the slope here. And it looks like if I can count down 2 boxes and over 1 box on my red line, I get the slope of the red line to be negative 2. Okay? And since I have the point that the point where, I guess let's call it the point of tangency, I can write y plus 1 equals my slope, negative 2, and then x minus 2. Okay, let's do a second one. Fancy equation, y equals 2 secant x at pi, comma, negative 2. So right here, that little maximum. So my tangent line is obviously horizontal, right? So that means it's going to be in the format y equals and then b, whatever, the y-intercept is, right? Since it passes through negative 2. Our equation of our tangent line this time is just y equals 2 because it's horizontal. So that's how we write them up that way. And we've got horizontal tangent lines. Okay? So let's kind of start to try to tie some ideas together from the other day. The other day we looked at the limit definition, right, of a derivative. So we took the limit as h approaches 0 of this function right here. We did x plus h squared plus 1 minus x squared plus 1. And then we divided that by h. And we figured out the result of that limit process. Do you remember squaring this, right? And then we canceled things out. And we ended up with this derivative. Our answer to this limit was 2x. Okay, so I'm going to talk about what that 2x is for here. So let's go back to this equation, y equals x squared plus 1. And let's kind of graph it up a little bit here. Here's that same parabola that we drew the other day. Okay, and what this 2x is it, again, we call f prime, we call this the derivative, right? And the case is, if I pick different values of x, let's say when x is 1, right? My tangent line has a different slope than, let's say, when x is negative 1, right? And then, of course, like we saw this example here, when my x value, right here, of 0, right, I get a tangent line that's actually horizontal. So the way that I can determine these slopes of these tangent lines is to use this derivative. So you kind of want to think of this little thought bubble here. Think of the derivative as a slope generator, right? It is a function that takes an x input and it tells you a slope output. So when I plug in 1, right, to the equation 2x, I get 2 times 1, which is 2. So that means the slope of this line is 2. When I plug in negative 1, I get negative 2. So that means the slope of this guy is negative 2. And of course, if I do 2 times 0, I get 0. And that matches up with our horizontal tangent line. Okay, now what we want to do is we want to avoid having to do that every time. That process is very long and convoluted, and we haven't even gotten any complex functions yet. This is just a simple quadratic. Okay, imagine if you had to cube it or raise it to the 4th power or had a power of 10. okay? That process is almost impossible for a human. So what we do is we start to think about some patterns that emerge when we do the limit process. So what I've got for you here is I've got a set of f, g, and h functions where I went ahead and did the limit process, right, and figured out what the derivative is here. Okay, so I did the limit process here and got g prime. I did the limit process on h and got h prime. And what I want you to start to do now is to think about what pattern you see emerging in order to go from a function to its derivative. Look at the coefficient here. Kind of look at what happens to the powers. This one makes it really evident. Okay. So what happens, right, is that we take the power, and that power in the original function comes down in front as the coefficient. So this 2 that's here is from that power of 2 there. And then we decrease that by 1 unit. So this is 2x to the first power. And then taking the derivative of 3x, we just get the number 3. Okay? This all goes back to the idea of the slope of each of these individual functions. Slope of x squared is 2x, slope of 3x, right? You just think about the function, literally y equals 3x. That has a slope everywhere of 3. Its derivative is 3 everywhere. So that's why its derivative is just a constant 3. Okay, same thing happened here. The 3 came down front, decreased the 3 to a 2, and then we just stole that coefficient of the slope of x, right, to finish off our derivative for g prime. And then here, when we have a constant in front, right, this became 200 because I took 2 times 100. That goes right here, and then we decrease the 100 by 1 to get 99, and then you can see that same process repeats itself here. Okay, this process is called the power rule. It's the most basic derivative rule we have. If you have x raised to a power and you want to know what its derivative is, you bring the power down in front and then you raise x to the n minus 1 as your new derivative. Okay, this notation here is a way to say take the derivative of what's in the parentheses. So when you see d dx, there it's a operation that says take the derivative of what's in here. So the derivative of x to the n is this format. The constant multiplier rule says the derivative of a constant in front times x to the n, much like what we saw over here. We take that constant times the power, and then we still decrease the power by 1. And then lastly, when we take the derivative of a number, right? So think about the function y equals 5, right? And think about what its slope is everywhere, right? At all of these little dots, that function has a slope of 0, right? The little tangent lines would be horizontal because the function itself is horizontal. So the derivative is the slope of those lines, which is 0. Okay. So these are our 3 rules that we're going to work with here for a bit of time in examples 1 through 4 down below. So starting out with 1 over x squared minus 1. This is our function. We're going to work on rewriting it in this format, and then we're going to take the derivative and put its simplified version here. So 1 over x squared, right, if we take that out of a rational format, that is actually x to the negative 2 minus 1, right? And then writing it as a power, I can take this derivative. It's negative 2x to the negative 3. Okay, remember I'm subtracting 1 on the power. And then the derivative of a constant is 0, right? So the derivative of minus 1 is nothing. Okay, so this is a fine way to write the derivative, or we got to recognize that that is the same thing and back in a rational format as this particular function. Okay, let's do another one. 4 root x minus 3x. That would be 4x to the 1/2 power minus 3x. Again, think of it like 3x to the first. So I'm going to bring the 1/2 times 4 to give me a power or a coefficient of 2, x to the negative 1/2, because when I take a 1/2 minus 1, right? As it says to do with the power, I get negative 1/2. And then over here, the derivative of 3x is just that slope of 3. Okay, we also have to recognize this is 2 over root x minus 3. Ew, minus 3. Okay. Next one, 2x, and that quantity is cubed plus x, so we're going to have to rewrite that as 8x cubed. Actually cube the 2, cube the x, and then take the derivative from here. So the derivative of 8x cubed is 24x squared. The derivative of plus x is just its coefficient, which is the number 1. So that's my derivative. Lastly here, number 4, this is negative x cubed over 4 minus 4 over x cubed. So one way to think of this is to think of this as like negative 1/4 as its coefficient. So the rewrite of this, I'm going to think of this as negative 1/4 x to the negative 3 minus 4x to the negative 3. Okay, same, just rewriting it in this column. And now we're going to differentiate it. So I'm going to bring negative 3 times negative 1/4 to get positive 3/4. I'm going to decrease this power by 1, so that becomes negative 4. Now I'm going to do negative 4 here times negative 3 to give me plus 12. And then x to the negative 3. Oh, wait a second. Wait a second, crazy lady. This is positive. Sorry. This is negative 1/4 x to the 3rd. So let's remix this here. Let's scribble a little bit here. So that should be negative 3/4 x squared, and then plus, like I was saying, 12x to the negative 4. And again, you can rewrite that x to the negative 4 as a positive power, in this version if you need to. Okay, now the last couple things that we are to do here is sine, cosine, e to the x, and ln of x. This is a bunch of derivatives here that we don't really have, a rule that they would abide by because they're not algebraic, right? So we're going to go ahead and just establish what these derivatives are. So I'm going to show you on your calculator how to determine what the derivative of sine x is. So let's hit y equals, and let's graph sine of x, and then let's hit the window button. Nope, God, I always do that. Let's hit the zoom button, and let's choose number 7, right? I'm going to look at the trig window. So here's the normal sine function, right? Should recall this from pre-calc. And then I'm going to give this calculator a fancy command here to draw for me what the derivative of sine looks like. Okay, so the derivative is going to be calculated by the math menu. All right, here's your math button. I'm going to go down to choice 8. See how that says n deriv. And then you see this notation with the d and the dx that we had up above. So I'm going to type in an x here. What I want it to take the derivative of is sine x, so that's what I'm putting in the parentheses. It's basically what's in y1. And then I want it to do it at every x value. So when it says x equals, I type in x again. And then let's graph and look at the red function and see what you notice. It's always a little bit slower to do this because it's calculating the slope everywhere and plotting it. Would you look at that? Do you know what the red function is? Yes, that is cosine. So the derivative of sine is cosine x. Whoops. There's no rewrite here, nor here, nor here, nor here, because these are non-algebraic. These we skip right over the rewrite and just go right to the derivative. Okay. Now if I type in cosine, if I type in cosine as my y1 and I ask in y2 it to take the derivative of cosine, you might think it's sine, but it's not sine. So now the original function is cosine. And let's take a peek at this red function and think about what that is. It, of course, goes through the origin like sine does, but it's flip-flopped, right? So the derivative of cosine is actually negative sine x. So it's opposite of that. Okay, I've got a crazy derivative rule for you here. We throw in e to the x right now. because it is its own derivative. The derivative of e to the x is literally e to the x. Okay, that's kind of an insane fact, but it's true, and we'll study that more closely in chapter 5. And then lastly, ln of x, right? The natural log is a function that we use a lot more than a regular log, okay? So remember that ln of x is log base e of x, right? That's what that means, and we just shortcut it to writing it as ln for natural logarithm. So the derivative of ln of x is 1 over x. Okay, so these 4 can't be figured out by a rule. They just have to be memorized. Okay, last thing then we're going to do today is look at 3 examples. We're going to tie back this beautiful little bow, this knot about finding the equation of a tangent line. So now that we have all these derivative rules, we want to be able to write equations of the tangent line just like I did before. So if I have a function 1 over x, and I know that the x value I want to calculate the derivative at is 1/2, first thing I write on my paper is f prime of x, right? I take the derivative. So I have to think of this in its rewritten form, which is x to the negative 1, right? And then I bring that negative 1 down front, decrease that power by 1, and then I might rewrite it so that if I plug in this 1/2, I have a better way to calculate it. So we now can do f prime of 1/2 is how we show plugging that in. And this is negative 1 over 1/2 squared, which is negative 1 divided by 1/4, which is negative 4. So remember that this is my slope. I've just calculated the slope of my tangent line. So what I'm missing right now is I know my slope is negative 4, and I know my x value is 1/2, but what I'm missing, right, is my y value. Well, that's the point of tangency, right? X comma y is actually on the function. So I calculate my y value by doing 1 divided by the input of x, right, 1/2, and that's 2. So here's the equation of a tangent line. Okay, I'll do one more with you and then have you try one on your own. In example 2, our function is now 2 cosine x, and we want to know the slope at pi thirds, right? So let's establish the derivative here. If that constant of 2 is in front of cosine, it's going to be a constant multiplier, so it's going to multiply through to the derivative, right? Derivative of cosine is negative sine x. So I wrote that kind of like a weirdo, but I think you know what I mean. So f prime of pi thirds is negative 2 times sine of pi thirds, right? So let's think about our unit circle. Sine of pi thirds, right? That's 60 degrees at pi thirds, right? So sine, right, has to be our y coordinate, so that's root 3 over 2. So I've got negative 2 times root 3 over 2, which reduces to negative root 3, and that's my slope of my tangent line. So I know this much already. I just have to go figure out, right, what 2 cosine of pi thirds is. So my y value is 2 cosine of pi thirds. We know that cosine must be of pi thirds must be 1/2, right? So 2 times 1/2 is 1. So that's the y value there. Okay. I'm going to have you guys try example 3 on your own.